Hello everyone, I am going to present you our new paper entitled Weight Reparametrization for Budget-Aware Network Pruning. In this paper, we introduce a new weight reparametrization to allow optimization of both network topology and weights at the same time, under budget constraints. Network pruned by this method does not require fine-tuning. I will first give you a quick overview about pruning and sparsity, then I will present our method and the results, and finally I will give you the key points of this presentation. About pruning and sparsity. Pruning is a group of methods that aim to design lightweight architectures. It is to say, architectures that has either a small memory footprint or a fast inference time or both. Sparsity is introduced by removing redundant or unnecessary weights of the network that is overparameterized. Pruning can be applied at different granularity. This is what we will see in the next few slides. Coarse-grained pruning refers to methods that remove either a subnet or a complete filter or part of it, for example, channels, columns, or rows. Fine-grained pruning targets weights or neurons. Our method belongs to the fine-grained pruning category, therefore we will focus on this one. Let's talk about pruning pipelines. Standard pruning pipelines are composed of 4 steps. First, the initial training of the full network. Then, the pruning criterion is applied to determine which weights are to be pruned. The next step is effective pruning, where the pruned weights are set to 0 and frozen. Finally, the weights are fine-tuned to compensate for the loss of performances. In such pipelines, the pruning criterion is applied after the initial training. As a consequence, the initial training does not take into account the final weight budget given by the pruning rate target. In contrast, our pipeline takes the final pruning rate as an input of the problem and it is used during the initial training. This results in the topology being optimized with the budget constraint from the start. It helps preventing disconnections in the network topology. Now that we have these elements in mind, I will give some details about our method. First, let's start with weight reparametrization. New weights, called W hat, are created, being the Hadamard product of the original weights, here called W, and H of W, H being our reparametrization function. W are the standard neural network weights. Now, let's talk about the reparametrization function that we call H. Our contribution is the formulation of this reparametrization function. Here you can see its shape. Let's analyze the different parameters of this function and their impact. H is numerically stabilized by adding +1 at the denominator. As a consequence, we need to add the two constants C1 and C2, which ensure that our function H lies between 0 and 1. H has a temperature parameter called T that controls the bandwidth of the pit. T is a learned parameter and it is optimized with SGT. We initialize its value to 100. N controls the sharpness of the falling and raising edges of the pit and its value is set and fixed to 4. Our reparametrization function soft prunes the smallest weights and preserves the largest ones. Now I will talk about our budget loss that aims to control the weight budget during training. To compute the budget, it is to say the number of weights used by the network, one would like to use the L0 norm. However, this norm is not differentiable. As a secondary contribution, we propose this budget loss in which we plug our reparametrization function H as a surrogate for L0 norm. This loss is composed of 3 parts. The current cost is the sum of all reparametrized weights and it's computed at each step. The target cost is the number of parameters that will eventually be kept. The initial cost is the sum of weight reparametrization at the initialization. We divide by C initial to ensure a better conditioning of the budget loss function. Finally, the budget loss is combined with the main task loss thanks to a parameter lambda. I will now present the results of our experiments. Here are the results for COMP4, VGG19 and ResNet18 networks on the CIFAR10 dataset. The 3 graphs shows that our method performs significantly better than magnitude pruning and our method is in a small margin of fine-tuned magnitude pruning. Keep in mind that our method does not need any fine-tuning after pruning. On TinyImageNet for a COM4 network, our method performed better than even fine-tuned magnitude pruning for very high pruning rates. Again, without the need for fine-tuning. Now I will sum up what we saw in this presentation. Here are the key points. We introduced a new weight reparametrization that acts as a regularizer and a saliency indicator, which induce sparsity by soft pruning the smallest weights. This reparametrization allows to optimize both topology and weight under budget constraints. Our method significantly overperforms magnitude pruning without fine-tuning and performs better than fine-tuned magnitude pruning for very high pruning rates on more complex datasets. This while our method does not need fine-tuning. Here are a few perspectives for our current work. First, evaluate our method on larger and more complex datasets. Then improve the performances to outperform fine-tuned magnitude pruning more consistently. And finally, assess the impact of the reparametrization function and test other functions. That's it. Thank you for listening.